Context here, we're going to start out by imagining the motion of a particle that is still recording, right? That's it. Okay. Along a line. So it can go back and forth along a line. So we're imagining a particle bouncing back and forth along a line. And we are going to imagine an axis that the particle is moving on. We're going to choose an origin. And typically, we're going to have the positive direction be to the right, negative direction be to the left. So standard stuff. And the function s is going to represent the position. The a and the b are at a particular time. So s of b is the position at time b. S of a is the position at time a. And first important word that we're going to learn is displacement. So displacement is going to be s of b minus s of a. It's the final position minus the initial position. The important thing with displacement could be positive, could be negative. Depends on where you start and where you stop. Okay, it's always right minus left. I shouldn't say that. It's not always right minus left. It's always terminal minus initial. It's always final minus initial. So if you start and finish to the right, then it's right minus left, and that's going to be a positive displacement. If you start and move to the left, your displacement is going to be negative. So it's always terminal minus initial, final minus initial, whatever you want to refer to it as. So your displacement can be positive or it can be negative based on the direction of the motion. Okay. Now, s of b minus s of a, well, heck, we have a mathematical way to calculate s of b minus s of a. And that is what you learned in Calc 1, called the integral. So the definite integral, couple things here. If we take the definite integral of the velocity from a to b, it will turn into s of b minus s of a because s prime is equal to v. Right? The derivative of position is velocity. So in other words, s is an antiderivative for v. If we integrate velocity, we get position. And the beauty of the definite integral is that it creates this s of b minus s of a instantly for us. So displacement, super convenient. We just do the definite integral from a to b, and that gives us our displacement. Okay. Stop me if you have any questions as we're going through. I can't tell. You all look like you get everything. So you got to tell me if you're not getting something. I can't tell. Okay, sometimes I can tell. Sometimes, but not always. The first test is always interesting. There's always someone I'm like, oh my God, I thought they had everything down. They didn't. Here is a graph of velocity on the left and absolute value of velocity on the right. So just a little bit of algebra stuff. So if we graph the velocity function, the velocity is positive until we get to that intersection point. And then over here, the velocity is negative. So if the velocity is positive, that means we're moving to the right. If the velocity is 0, that means we stopped. And then if the velocity becomes negative, then we're moving back the other direction. Okay, so this is a picture of velocity, not distance or displacement. That graph is a graph of velocity. But what we know geometrically is that the integral geometrically finds the area beneath the curve. So if we were to integrate velocity from this point A to this point here, that geometrically is just the area beneath the curve. Mathematically, we already figured out that if we do s of b minus s of a, that's going to give us the displacement on this interval. So that is a geometric way to think about this. If we keep on integrating and go all the way to b, the integral is going to have the effect of doing this upper area minus this lower area. When I use the word area, make sure you're thinking positive. Sometimes they'll talk about signed area, and a signed area could be negative, but if we just use the word area, it means, positive number. So this area minus this area, that will give us displacement. So the integral is automatically going to do that for us if we integrate from a to b. It's going to take all the stuff up top and subtract all the stuff below. That'll be our displacement. if we take the absolute value of velocity, the absolute value of velocity is speed. And if we integrate speed, so mathematically, if you take this function and you take its absolute value, it makes all the y values positive, the ones that were negative, so it reflects it through the x-axis. That's now distance traveled. Okay? That is a piecewise defined function, though. And it's not trivial to integrate a piecewise defined function. To integrate a piecewise defined function, you integrate piece by piece. Right? You have to integrate piece by piece. Just like the derivative of a piecewise defined function, take the derivative of each piece. So whenever you see an absolute value function, it's very easy. A lot of people just have this, oh, it makes it positive, which it does, non-negative. Does make it positive if it was negative, but the math behind it is that it's a piecewise defined function. When we take the absolute value of v, this is two things. This is either equal to v if v is greater than or equal to 0, but if v is less than 0, then what do we do? What is the function output going to be based on the v? Negative v. If v is negative, the math behind it is that you multiply by -1 to make it positive. So that's what's happening there. So if we wanted to differentiate this piecewise defined function, we would differentiate this piece, differentiate that piece. If we wanted to integrate it, we would integrate this piece, greater than or equal to 0, integrate that piece. Okay, so really important that when you see that, you realize you should be thinking, oh, two pieces. Obviously, a piecewise defined function can have more than two pieces, but for us, mostly it's two pieces. That or that. Okay, so let's take a look at this example here. So again, in our mind, we're just imagining this particle bouncing around on a line. This is a picture of its velocity. So this tells us that the velocity starts negative. So that means the position is moving left. This picture does not tell us where we start. We do not know what S of 0 is. We know that V of 0 is 0, but S is not in this picture. S of 0, we don't know. When we look after 2 seconds, we can say, oh, we're 20 units to the left of wherever we started. But this picture does not reveal where the starting point was, where the initial point was, where the origin is. So when we look from 0 to 2, okay, yeah, we're 20 units of whatever distance, 20 meters, 20 inches, 20 feet, left of where we started, but this picture does not tell us where we started. So we need more information if we wanted the coordinates of the point after 2 seconds. If they don't tell us what S of 0 is, all we can say is 20 units to the left. All right, so super important to get that idea. So this says on what intervals is the object moving in the negative direction. So when we look at this, what are the 2 intervals where it's moving in the negative direction?
0 to 2.
So 0 to 2, and I'm going to use parentheses because at those endpoints, what direction is the particle moving?
It's neither.
It's got a velocity of 0, so it's stationary. So we don't want to include that because it's strictly saying moving. Now sometimes people are a little sloppy with endpoints, so you just be careful with the endpoints. Technically, that's the right answer. But there's sometimes in my math, like maybe they might include it when it probably shouldn't be. Or just be aware that if you type that in and then it says brackets, this is correct, right? Because we know at 0, 2, 4, and 6, the particle is not moving. So if the question says moving in the negative direction, it's not moving in the negative direction if it's stationary. But just be a little careful. Math and physics books sometimes aren't as careful as they should be. Okay, so what is the displacement on the interval 2 to 6? So 2 to 6, so we're looking in here, and we want displacement. Displacement is the definite integral. Geometrically, it's upper area minus lower area.
4.
So we're going to get, exactly, we're going to get 4. So we'll do 14 minus 10. So that'll be our displacement. C, what is the total distance traveled by the object over the interval 0 to 6? So now we're going to go 0 all the way to, ooh, that's probably a bad color. So 0 to 6, let's just keep using yellow. 0 to 6. Total distance, so we're going to integrate the speed function, which is the absolute value of velocity. Geometrically, that just makes all the negative, the signed area positive. So yeah, we'll go, so we're going to have 20 plus 14 plus 10. So there is our total distance traveled in that interval. What is the displacement from 0 to 8? Negative 10. Upper minus lower. And then describe the position of the object relative to its initial position after 8 seconds.
10 units to the left.
10 units to the left. That's all we can say, because we don't know the exact position when we started. So all we can say is 10 units left of the initial point. Initial position. Okay, all right, we're doing math.
Is it true to say that velocity is the net area and then speed is the total area?
You could say that displacement is the net area.
Okay.
Displacement is the net area and distance is the total area.
Okay.
You could do that. Yeah, because net allows for that negative quantity. So net we would think of as upper minus lower. For sure. And when we start to generalize this, if we look down to this slide right here, so when we're talking about a particle moving or just distance displacement in general, displacement means net. That means net automatically. Whereas if we go to a quantity that's not distance, here we would say, let's see, so if this was, let's say volume, this would be net volume. But for displacement, net displacement, or net change in position is displacement. So for that one particular special case where we're talking about distance, we use displacement as that word for net change in position. Okay, so let's see. So we've talked about most of these things already. So velocity is the derivative of position. The change in position, which is also called displacement, is our definite integral from A to B. Integral of speed is distance traveled. So absolute value of velocity is speed. And you have found position from velocity in the past. You've probably used a technique called the antiderivative technique. The antiderivative technique is where you integrate with an indefinite integral and you get a plus c, and then you take your initial value and you plug it in and you resolve the constant. So that is one way to find position from velocity. Generally speaking, this approach, which they call the fundamental theorem of calculus technique, generally this method is preferred because it generalizes really nicely. Can you use the other technique? Yes, but this gives you a kind of a better concept of what's going on. So if we say S of t, we're saying, well, what is the position at a future time value? Well, it's where it starts plus the displacement. So we just did that one example where we did all this displacement stuff. And if you add the initial position to it, then you're going to get that future location. So you can think of the future position being the current position plus any displacement that happens. So this is a more elegant way to think about future position. So let's do a couple of examples where we use this technique and we also use the technique that I'm sure most of you have used, called the antiderivative technique. Okay, so we've got an object moving along a line with velocity v, time is measured in seconds, velocity is meters per second. So determine when the motion is in the positive direction and when it is in the negative direction. So we want to do that first. Generally, a graph is an easy way to look at those subintervals and figure that stuff out. So if we can graph this quadratic, that's probably going to be the slickest way. We know that the graph is a parabola because it's a quadratic, so we know that. And we know that it's going to open which direction? Open up because it's positive. So if we knew the two zeros, we could find the vertex would be right in the middle. That would be an easy way to graph this. So what I'm going to do here is factor out the GCF. So we are going to see that the zeros are 0 and 2, which tells us that the vertex has to be somewhere in the middle. And we don't care exactly what the coordinates of the vertex are, but this case, all we really want here is the general shape. So if we look at this, we know that the zeros are at 0 and 2, and we're only going out to 3. And we know the vertex is at 1 comma minus something. Doesn't matter where. So if we graph this, it's going to look something like that. We just want a relative shape so that we can kind of figure things out with a picture here. So we know now we can answer part A, determine when the motion is in the positive direction, when it's in the negative direction. So part A, in the positive direction,
3 to infinity.
well, we're only looking from 2 to 3. So this tells us that,
So 2 to 3, yeah.
so 2 to 3, so we're stopping right here. But now, with that endpoint of 3, should we exclude or include it? We are going to include it because it's still moving in the positive direction, right? At 3, it's not a 0.
And because it's t less than or equal to 3.
Less than or equal to 3, so it's being included there. And then negative direction. What should our interval be for the negative direction?
0 to 2.
0 to 2. Do we include any endpoints there? Ooh, that was a terrible comma. So, yeah, we will exclude both of those endpoints there. All right. Part B says find the displacement on the given interval. So displacement, that's the easy one. We just do the math. We just integrate. Integrate from 0 to 3. That'll automatically do the upper minus lower area for us. So the displacement, which we don't have a simple symbol that we use for displacement other than the integral. Right? For distance, we usually use a d, but for displacement, we're just going to have to write the word displacement. So displacement is going to equal the integral from 0 to 3. And we will be integrating the velocity function, so 3t squared minus 6t. And our differential is the dt. Integrating a polynomial, simplest of all antiderivatives, add 1 to the exponent, divide by the new exponent. It's crazy that that works. Plug in 0 and get nothing, so we really only have to look at the contribution from the 3. So we're going to get 27 minus 27. So we get 0. So that is the displacement. So what that tells us is that it's like going to school. You start from home, drive to school, drive back home, displacement is 0. clearly the distance traveled is not 0. But that's the idea. So displacement is 0. Find the distance traveled. If the displacement is 0, that tells us that this area down here and this area up here must be equal. We could certainly integrate. We could do what I said that we normally do with a piecewise defined function, and maybe we should do that, maybe not. But we know that these two areas are equal. So what we could do is integrate from 0 to 2, and then integrate from 2 to 3, and multiply this one by -1, and we get the total area. Or we could just be clever and say, oh, well, if they're equal, we could just integrate one of them and double it. That seems like the more clever way to do it. So let's do it that way. So the distance traveled, we'll call it d, will be 2 times the integral. Now let's focus on the 0 to 2 one. So if I do 0 to 2, okay, there's the function, the velocity function. But if I'm integrating 0 to 2, that's a negative velocity, so we have to multiply that by -1 to make it positive. So this is going to be integrating -3t squared plus 6t dt. So that would be one way. You could also do 2 times the integral from 2 to 3 of the function, not multiplying by -1, because the velocity is positive between 2 and 3. So let's just do the math here. So once again, add 1 to the exponent, divide by the new exponent. Does that look okay? That'll be 0 to 2. Very sensitive, this board. Plug in the 0, we get 0. 2 is the only thing that matters, so -8 plus 6 is -2. Wait, what? Something's wrong.
Isn't it plus 3t squared?
Oh, that was bad integration. Thank you. 3t squared. Oh, thank you. If something doesn't make sense, double check. That did not make sense. Distance traveled has to be positive, cannot be negative. So we knew something was wrong. Okay, plug in 0 again, we get nothing. So now we have -8 plus 12, which is 4. So we get a total of 8.
And that 2 is only there, that 2 on the outside is there because you're multiplying.
So we're doubling, so our focus is just on this area from 0 to 2. And so if we found that area, the total area would be 2 times that because the two areas have to be equal.
So the bottom would be 4 times 2 because you included the 2 in the equation?
So this is our total distance traveled, so each of those will have an area of 2.
All those you have.
Yeah, does that make sense? Each of those pieces will have an area of 2. So we doubled the 2 to get 4. All right, let's try this one. So again, graph is important. A graph reveals a lot of information. Helps you orient your thoughts. Exponential function. You should be able to graph exponential functions. This is an exponential growth or decay.
It's 8.
Oh, I'm sorry. Did I multiply wrong?
It's 4.
Oh, it's 4 times 2. Sorry.
Yeah.
Thank you. Now I understand what your question was. Now I understand. Sorry about that. Yeah, 8. So it's 4 and 4. Each piece is a 4. Total is 8. Yes. Yeah. Arithmetic. Who thought we were going to have to use arithmetic? Okay, so exponential decay, because the exponent is negative. We know that exponential growth, up to the right, exponential decay, down to the right. And we don't have to get more precise than the shape and the y-intercept. That's all we need. So exponential growth like that, exponential decay like that. That's all we need. So we know that this is sweeping down. We know it's not crossing the t-axis, right? That's always positive. That can never be negative. E is 2.7. You raise that to a power, that can never be negative. An exponent can never make an exponential expression negative. So that's always positive. If we plug in the 0, e to the 0 is 1. So our shape is going to be something like that. And this is going to be an asymptote. So just a general sketch. And this intercept right here we said is at 50. So there is our general shape. This tells us that the velocity, and we don't even care about to the left of 0. We're only going 0 to 4. So when we look at this interval 0 to 4, we're only looking in here, and the velocity is always, so the velocity is always positive. We're never going to have a velocity of 0, so it's always positive. And the velocity, with the velocity, did I hear someone say velocity is increasing? The velocity is decreasing. Velocity is decreasing. As time is going by, the velocity is less and less. Okay, so the first question said positive and negative. And what do we have here? So for positive velocity, 0 to 4, and we're going to include both endpoints because we're still moving at both those endpoints, both those t values. And negative never. So that was part A. And then part B was find the displacement. Oh, we get to integrate an exponential. So the displacement is the integral of our function. So 50 e to the minus 2t dt. And we're integrating on the closed interval 0 to 4. Okay. In Calc 1, at the very end of the semester, you know the part of the semester where you remember things most clearly, the last 2 weeks, last week, you learned an integration technique that's the most important integration technique up to this moment. And that integration technique is?
The chain rule. Fundamental theorem.
Begins with an S.
Substitution.
Substitution.
Use substitution.
U sub.
Okay.
Substitution. That's the most important one. The chain rule is going to come into play there. Let's do it using this elementary Calc 1 technique, and then we're going to show you an elegant way to do it by reversing the chain rule. And we are going to be integrating this type of stuff so frequently that's really important that you don't use substitution every time. Let me show you both techniques. So u substitution, your u is generally the exponent, the angle, one of those, something obvious, what's in the square root. It's usually the thing that's, kind of a pain, the exponent here. So if we let u equal negative 2t, then we take, so you can think of this in a couple of ways. If we take the derivative of u with respect to t, we get that. If you multiply both sides by dt, you have that du is negative 2 dt. Now, hopefully, most of you are probably to the point where you just go straight to that. But the idea is that first you're differentiating, and then you're breaking apart that derivative into two differentials. So with substitution, you have to substitute for the variable, and you have to substitute for the differential. So that's going to be our step there. That is going to be how we can turn the dt into a du. So one more step here. If we divide, if we want to isolate the dt, we're going to write the isolated dt as du over negative 2. Now we can convert. So we come up here, this integral, it's still a definite integral. We're just going to start plugging things in. That's going to be 50 e to the u, and then du over negative 2. Now we look at the limits of integration, 0 and 4. Those are t values. The differential is indicating what the letter is for these values here. So t equals 0, t equals 4. Our differential is now u. So we want to convert. We want those limits to reflect the variable. So we come down here. This is the magic right there. This tells us how you exchange t's for u's. So you hand in a 0 for t and you get out a 0 for u. So that is our lower limit. You hand in a 4 for t and you get out a negative 8 for u. All right, so that's our new integral. Generally speaking, we like to think conceptually about an integral as integrating from left to right. That looks like we're going from right to left though. What can you do to change that if you wanted to?
Negative and invert the sign.
Right, so if you switch your limits of integration, you toggle your front sign by -1. So we could make this -8 to 0. Let's do the math in here. 50 divided by -2. Let's just leave it in there for now. And then if we do that minus out in front. So as soon as you switch your limits of integration, plop a -1 out in front, then it's equal. Now you don't have to, you could integrate like that. You can integrate right to left, it does not matter, but just as a reminder. Okay, so now let's just simplify this a little bit. Remember that you can factor constants through. Constants can move in and out of derivatives, they can move in and out of integrals. So we have that, and then what is the antiderivative for the exponential function? It's itself, e to the u. -8 to 0. So this is going to be 25 multiplied by upper limit first, e to the 0, which is 1, minus, so this is fundamental theorem of calculus, antiderivative evaluated at upper minus antiderivative evaluated at lower. So now minus e to the -8. So there is whatever we were finding, displacement. There is our displacement. Is that a positive number?
Should be.
Is it?
No.
It isn't?
It is, yeah.
It is. How big is e to the -8?
Very small.
Not very big, right? E to the -8 is super small. Yeah, yeah. Because of that negative, this is fractional. So we're subtracting out something that's less than 1. So it will give us positive displacement, which we expected because the velocity is always positive. Okay, so there is our displacement. All right, so that is how, if you were in Calc 1, that's how you would evaluate that integral. You are now in Calc 2. You should be evaluating this integral slightly differently. So here's the technique that I am going to encourage you to use. And I refer to this as the reverse chain rule. You are not going to see that in the book. But we're going to call this the reverse chain rule. I'm going to write it RCR, reverse chain rule. And we will do this no less than 100 times this semester. So the reverse chain rule. When your substitution is linear, the integration of this is itself divided by the derivative of the exponent. So, chain rule. Remember chain rule. If somebody said to you, if you had e to the 4x, what is the derivative here?
E to the 4, e to the 4x.
E to the 4x times 4. It's itself multiplied by the derivative of the exponent, right? That's the chain rule. The reverse chain rule, if we integrate e to the 4x, the integral of an exponential is itself divided. That is the reverse chain rule. When you're differentiating, you multiply. When you're integrating, you divide. Instead of doing all of that, if your substitution is linear, this is the only time that the reverse chain rule works. If the substitution right here is linear, not constant, not quadratic, if it's linear, this works every single time. So that tells us then, using RCR, that this is going to be 50. Integral of a constant just floats. The integral of an exponential is itself divided by the derivative of the exponent. Yeah?
You missing 4s over here, right? Just for clarification. On each expression, so the 4s would cancel out and it would get you e to the 4x. Right?
Here?
Yeah.
No, this is right.
Is it?
the integral of an exponential is itself divided by the derivative of the exponent. How do you check? If you were to take the derivative of this, the derivative of the constant 1/4, is that just a multiplicative constant, so it stays.
Yeah.
And then you'd have 4e to the 4x, and those cancel, and you get back to your e to the 4x. That makes sense?
Yeah.
That pen, junk. So let's finish this off. So we get negative 25. All right. Plug in the upper limit, plug in the lower limit, take the difference. Do we have no women in this class?
Yep.
Whoa. Well, we have one, but she's not here.
That's why we don't last long.
Wow.
Oh.
That's unusual. Wow. So this is e to the minus 8 minus 1. And if you wanted to distribute this minus sign just so that it looks identical, that's important. Then we do that. Those are equal. In math, being efficient is super valuable. That is efficient. That is a runaround. But this is why this is all going to work. If you did this a few times, you would realize, oh yeah, right here, I'm just dividing by the negative 2. Right? And that's how it is every single time you have a linear substitution. Quadratic substitution, this is not going to work. So reverse chain rule is a special case for when the substitution is linear, and it will work every single time. So that's how you should be doing it. The integral of an exponential is itself divided by the derivative of the exponent. That is going to be the way. Okay, so part C, this was displacement. And then part C, what about distance traveled? Same, different, more or less? Same, right? Because the distance and the displacement have to be the same if the velocity is always positive. So this is going to be exactly the same. So 25 times that. And I think they probably gave us units. Did they give us units in this one? A lot of times in math they don't give us units, but sometimes they do. So we have t and we have meters per second. So this is going to be meters. This is going to be meters for those two, for displacement. And a was just intervals, so. All right, any of that stuff? Any questions? Any of that stuff? Yeah?
You know that previous example, how do you go from 75 to 25?
I know, it said 25, it's just written weird.
This right here,
Yes.
that's a 2.
Oh.
Sorry. I try to. That's a 2.
That's why it's important to ask questions.
Yeah, absolutely. Yeah. Trying to get used to this little pen on this big board. It feels like I should be using a marker that's bigger. All right, let's question.
Well, I've taken Calc 2 before, but whenever you were doing reverse chain rule, weren't we supposed to do -1 on the...
That is when you're using the power rule.
Oh, okay.
So the power rule is what you use when you have a polynomial. You know, so you add 1 to the exponent, you know, do that kind of thing, divide by the new exponent, or if you're differentiating, subtract 1.
Sorry.
Exponential is a different category, right? So we've got our polynomial integration, which was power rule, and then our exponential integration, which is chain rule, or reverse chain rule, depending on how you think of it. Okay, so normally we will take a break after 1 hour, so let's do that, but let's only take 5 minutes. Normally we'll go with 10-minute breaks, but because we lost the first half hour, we'll just do a 5-minute break and then we'll finish up chapter 6. Not chapter 6. Section 6.1. Chapter 6. No. Got to get into the flow here. The dots. Okay, so another one here. So we want to do the same type of thing. Moving along a line, our velocity function is a trig function. Once again, graphing the trig function or graphing the velocity function so you have a sense of what's going on is really helpful. So make sure you can graph your basic trigs. And we know that sine is going to look like that. from 0 to 2 pi. So pi is in the middle, 2 pi is on the right end, 0 is on the left end. So there's a graph of sine of t 0 to 2 pi. Okay, so determine the position using the antiderivative method. So that's the method you're probably the most familiar with. And then also do it with the FTC method. So let's do it both ways. So the way that you are most familiar with it is that position is the integral of velocity, and instead of using a definite integral, you're going to use an indefinite integral. So the antiderivative method, you use an indefinite integral. No limits of integration. The integral of sine, antiderivative, minus cosine of t, plus c. One thing that's helpful in OneNote is that there's this separator thing under the draw tab. Let's see, where is it? Right there, insert space. If you need space, this tool will actually move, it will move, I have it in 2 places here. It will actually move ink. So if you use this tool right there, that separator, you can move stuff pretty easily, or you can close stuff also. If you click lower and drag higher, you close stuff. So that's a good tool if you're in the worksheet and your things are getting funky. You can use that tool. Okay, so now we have position, but we don't have the constant resolved yet. So we have to resolve the constant. So we use some sort of initial value that's given. So they tell us that S of 0 is 1. They tell us the initial position is 1. So what we want to do then is come down here and we say, okay, S of 0 is 1, so the position is 1 when the time value is 0. So then we're going to plug in 0 for t, and that will allow us to resolve the constant for this particular initial condition. Cosine of 0 is 1, so we end up with c equals 2. And then we come up here, and so our conclusion is that the position at time t is going to be negative cosine of t plus 2. So that is the antiderivative method. Should look familiar. Any questions on any of those steps? So this is using antiderivative method, so that is A. Now the fundamental theorem of calculus method, question?
Yeah, if you could just explain how you went from the 1 equals the negative cosine 0 to 2 equals
Oh, yes, because cosine of 0, what is cosine of 0?
1.
So that's negative 1 plus c, and then add 1 to both sides. Make sense?
Yes.
So there we have the position function using the antiderivative method. Let's go ahead and use the fundamental theorem of calculus method. So part B, what we say is that the future position, so we're thinking of S at some time in the future, that's going to be wherever it started, so that's the initial position, plus the displacement on the interval. And the interval in this case is 0 to t. Right? We don't know what that t is. So that future value is at whatever t is. So we want to know what is the interval, or what is the integral from 0 to t of the velocity function. Question? So that's what the position will be at 2 pi, but we can imagine starting here and we want to know what the position is at every value of t. So certainly if we want to know where is it after 2 pi radians, after 2 pi seconds, we would plug in the 2 pi. But the S of t is going to give us that position wherever, for any value of t between the 0 and the 2 pi. So yes.
Because the question's asking for the position function, not just the solution.
Correct.
So
Right.
it's a general function.
Yeah. Okay, so now we have to be a little bit careful here. Normally, we're just going to drop the velocity in, but we've already used the letter t to represent that right endpoint as it's moving. We don't want to use a t again. And we know that the letter in a definite integral is just a dummy variable. It disappears, right? It doesn't stay. It disappears. So we can use whatever letter we want. So I'm going to use an X. It's so creative. So instead of a T, I'm going to use an X because we don't want to get confused with the T as a limit of integration and T as an integration variable. And everybody remember the whole dummy variable thing, right? If we integrate x squared from 0 to 2, that's not a variable. It's a dummy variable because it's not going to stay around. When we integrate, we get x cubed over 3 on this interval 0 to 2, and we get 8/3. There's no variable here. Right? That dummy variable is just a placeholder to evaluate and get it's a number. This is a constant. That's not a function. That's a constant. I guess you could say it's a constant function, but it's not a function. There's no variable in it. That dummy variable is just there for a moment. It's a placeholder. So we can use whatever we want for that placeholder. X, gamma, whatever. Zeta. Okay, so now we plug in what we know. S of 0 is 1. And then if we integrate sine, we get negative cosine of x. And that negative cosine of x is evaluated on the interval from 0 to t. Is that one part of the antiderivative?
No.
No. It is s of 0. The antiderivative for sine is negative cosine x. So when we do this substitution in here, when we replace the x with a t and the x with a 0, we do not include the 1. If you did, then you'd subtract the 1's away and it would vanish. Right? You would have this whole thing at t minus this whole thing at 0. The 1's would disappear. We don't want to do that. The antiderivative is just this piece. So that piece right there is what we're substituting. So we're going to get minus cosine of t. That's the upper limit of integration plugged in. Minus the antiderivative evaluated at the lower. So minus of minus is plus cosine of 0, and cosine of 0 is 1. So this will give us 2 minus cosine of t. And of course, you better get the same thing, which we do. So either way, on the test, I don't care which technique you use. If you can get it one way or another, that's totally fine. This is the preferred technique. It's much more elegant. You're going in one direction. You're not figuring out something and then plugging it in and figuring it out and then substituting. Like, this works fine. Totally fine. This is the way you're going to see it done most of the time going forward. Okay, let's try this one. So that doesn't work on this board. Okay, so let's take a look at the answer. So this is another function that doesn't just have a t inside of it. So we're thinking about u substitution. We're looking at angles and exponents and stuff inside radicals. So if we're going to integrate this, we would, in Calc 1, do u substitution. We're going to be a little more clever, though, in Calc 2 and use reverse chain rule. So the position at a future time t is going to be the initial position plus the displacement on the interval 0 to t. And then we have to throw our function in there. We don't want to confuse the t's, so we make this letter of integration the dummy variable in x. So that's how we find future position. So future position is going to be the initial position, 1. They like using 1 as the initial position. Now, if you were going to use substitution, you would let u equal that angle. This angle is linear. And whenever there is a linear substitution, RCR, reverse chain rule, every single time when it's a linear. So here's how we're going to do it with reverse chain rule. So the 3's just coming along for the ride. Constants factor out to the front. Integral of sine is negative cosine. Integral of sine, negative cosine. So we have negative cosine of the same exact angle. If you were doing a derivative, you would then multiply by, but we are doing an integral, so we divide by pi. So we'll just put it out in front right there. So that is reverse chain rule. The integral of sine minus cosine, same angle. Derivative of angle is pi. Divide by that for reverse chain rule. And then we have our limits of integration, which are 0 to t. And then we just have to plug in correctly. Again, remember that this is the antiderivative here. The antiderivative does not include the 1. So this is the antiderivative. That is where you're plugging the t and the 0 into, not the 1. Dustin?
Did you just put parentheses or brackets around that or something?
Yeah, absolutely. If you want to distinguish it, absolutely. Absolutely. And we probably should. The book, they don't do it usually, but it's not a bad idea. Not a bad idea at all. So first we're going to plug in the t, and we are going to end up with minus 3 over pi. That minus sign can come out in front and combine with the 3 over pi. And then we have cosine of pi t. And now we subtract off antiderivative at 0. Well, the antiderivative is negative, so we have a minus thing. So it's going to be positive. We still have the 3 over pi in front. And then we have cosine of 0. And cosine of 0 is 1. Let me just write it as cosine of 0 for a moment. So there it is. And if we simplify this, that's going to be a 1. And maybe we want to put the constants all out in front. So maybe we would write it 1 plus 3 over pi minus 3 over pi times cosine pi t. So this is our position function at time t. It's our position function. And then if we wanted the position at a particular t value, we just plug it in for that t. So if we want the position at time 0, plug in a 0. We know that we're going to get a 1. If we want the position at 2 pi, plug in a 2 pi, get whatever we get.
So when you're plugging in 0, what happens to the pi?
Cosine of 0
Okay.
will be 1, and then we'll have 3 pi minus 3 pi, which is 0, and we get back to the 1 as our initial position.
Okay.
Is that tracking?
Yep.
So if we wanted the position at 2 pi, we'd be finding cosine of 2 pi squared, which is not a special angle, so we would just have to leave it as that, or get an approximation, if that's what they wanted. So we can do the same thing that we just did with position. We can do it with velocity. We know that position is integral of velocity, and we know that velocity is the integral of acceleration. So we can just do the same thing, but one step deeper in the position, velocity, acceleration sequence. So the future velocity, or the velocity at time t, is the initial velocity plus, now we don't use the word displacement here, we're thinking of this as the net change in velocity. The integral of acceleration is going to give us the net change in velocity. Could be positive, could be negative, who knows. But same idea. So instead of S and V, we have V and A. Same idea. And we can generalize this even more if we step out of the classic physics application. We could replace whatever is inside here with a Q. We can think about Q as a general quantity. Could be population, could be money, could be whatever. And if you subtracted this value over to the left, you could write it this way and call it the net change in Q is going to be that integral right there. Or you could just talk about it in future value context. The future value of Q will be the initial value of Q plus the net change in Q. So, either way. All right, so that is all well and good. So let's try it. So we have acceleration and we have velocity. So now we want to find the velocity function. So not the distance, not the position function, but the velocity function. So the velocity in the future, some t value, it's going to be wherever it started. The velocity in the beginning there was velocity. We call it v of 0. And now we want to add the net change in velocity, which is the integral of acceleration. So the net change in velocity, we integrate acceleration on the interval from 0 to t. The acceleration is our classic. Oh, I don't want to use a t, that gets confused up here. We'll use an x or whatever you want to use, a y. So that is our setup to find a function for velocity based on acceleration. Not too crazy. V of 0 is 50. Then we integrate this, and when we integrate this, we get negative 32 times x from 0 to t. That is going to give, I guess when we plug in the 0, so if we wanted to take Dustin's advice, if we wanted to, we could put a plus and then brackets or whatever. I can't squeeze it in easily, so I'm not going to do it. So if we plug in 0 here, we get 0. If we plug in a t, we get negative 32t. So now we have our velocity function. So that is our velocity function. So that would be meters per second if they gave us units. Okay. So now we have velocity as a function of t. Now they want us to then go again all the way back. So we're starting at acceleration. It takes 2 steps to get back to position. So then the future position, or the position at time t, well, it will be wherever the starting point is, the initial position, plus the displacement, which is the net change in position. So that's going to be the integral from 0 to t of our velocity. Don't want to use a t again, so we're going to use an x. And that'll get us all the way back to position coming from acceleration. Initial position is 0. That's given, so that's a 0. And then we integrate. So we do our power rule. Add 1 to the exponent, divide by the new exponent. And then we'll end up with 50 minus 16 t squared. So that's our position function.
50x.
50t.
This right here is a t, thank you. Yeah, when I integrated here, I dropped the t, or the x. So this should be a 50x, thank you. Right there, it should be an x.
And then we'll end up.
And then that's
Get
gonna,
up as 50t.
yeah, it's gonna change this over here to 50t. We plug in the 0, we still get 0, so 50t minus 16 t squared, there we go. Thank you. Good catch. Okay, you all try this one. So same thing with this acceleration function. Find the velocity as a function of t, and then use that to find the position as a function of t. And I'll leave that one up there so you can model it. Let me know if you need a nudge. So again, if you want to use that antiderivative technique, you're more than welcome to. Or try to get comfortable with the fundamental theorem technique. Any theorem called the fundamental theorem feels like something you should embrace. Fundamental theorem. Not just any theorem. The fundamental theorem. Oh. It's too cold.
Yeah,
I can't believe they delay us half an hour because it's a little cold.
yeah.
We live in Colorado.
It's the warmest it's been in like 3 days.
I know. It's warmer than it's been the last 3 days. I went skiing yesterday. It was minus 17.
What is this last lecture? I mean, no, Celsius would be better.
Yeah.
So, using the thing you talked about earlier, reverse chaining, the integral of e to the negative x is then the e to the negative x divided by negative one.
Oh, yeah.
Negative e to the negative one.
Beauty. Beauty, beauty. All right, I'll. Ooh, not with that.
It's not plus 0, it's plus 1. No, it's 0. Oh yeah, it's 60.
Divided by 1.
So that should be your first line there. The future velocity, initial velocity, plus the net change in velocity, which is the integral of acceleration. And v of 0, the initial velocity is given to be 60. And here's our reverse chain rule. So that exponent is linear. It's a linear function of x. Its derivative is -1. So the integral of an exponential is itself divided by the derivative of the exponent, divided by -1. That just changes the sign out in front. And that will go 0 to t. So we're going to end up with 60 minus e to the minus t, minus a minus, which is plus, e to the 0, which is 1. E. Everyone agree with that, or you need some? So here's our antiderivative. When you plug in 0, you're plugging in the lower limit, so it's always minus the antiderivative at 0. So minus a minus will make that a plus.
And we could just, I have a question, can we just like then ignore the c or the plus c?
There is no c when you have a definite integral. You could, if you wanted to, if you were so inclined to put in a plus c, but then you're going to have a plus c for both, and then they would subtract off and go away. But yeah, so for a definite integral, we do not need a plus c. And then the future position, so future position, s of t, will be the initial position, s of 0, plus the displacement. Displacement is 0 to t, and once again, we have to change the t to some other letter. I'll just be simple and pick an x. So does that all look good for general position, future position? Initial plus change. So s of 0 is given to be 40. So we're going to have 40, and now let's see if we can integrate. Okay, 61x, and then minus the integral of an exponential is itself divided by the derivative of the exponent. So it's going to make it plus e to the negative x 0 to t. Our, let's see, antiderivative is this. So we're going to have 40 plus 61t plus e to the minus t. So there's the upper, so this piece right here is the upper limit of integration substituted in. Now we subtract off antiderivative at 0. So subtract off 0 and then subtract off 1. So our final answer, 39 plus 61t plus e to the minus t. Future position. That's updating pretty quickly, huh?
Yeah.
It's amazing how fast it's gotten. Is anyone else looking at it on OneNote? It's coming up pretty fast for everybody.
Few seconds late.
A few seconds or a few milliseconds?
Seconds.
Seconds.
I don't know, it's a few milliseconds for me.
Milliseconds for you? Yeah, Gerardo's look like milliseconds too. Goal, get to microseconds. Okay, any questions on that?
Yeah, where'd you get the -1 from?
So,
Plug in 0?
yeah, so this is our antiderivative there. So here is the antiderivative evaluated at t. And then we subtract off the antiderivative evaluated at 0. So we're putting in a 0 there, which is 0. Plugging in a 0 there, e to the 0 is 1. And we're subtracting that off.
Oh, okay.
Make sense? All right, let's try one more. So just a general quantity instead of a distance, velocity, acceleration thing, we'll just do a general one. So here we're dealing with foxes, and we've got a population, it's fluctuating, blah, blah, blah. We want to know what the future population is. That's what we want to know. Now this is kind of worded, in my opinion, backwards. Once we find P of t, to find the population in 15 years, we plug in the 15. Right? That's the whole point. You figure out a formula that represents the future population, and then you plug in your t values. So we're going to do part B first. We want to find P of t. So P of t, we're just going to go through that same general argument. The future population is the current population, the initial population, plus the net change in the population. And the net change in the population is the integral from 0 to t of the population's derivative. But we're going to put in an x instead of a t so we don't get confused. So that would be our formula. So that's just generalizing what we did with velocity and position. So then our future population is, how many foxes did we start with? 35. Thank you. So 35 plus the integral from 0 to t. Now in here, we're going to plug in our p prime and just replace the t's with x's. So we're going to have sine by x divided by 5 dx.
5x plus.
So now we have that whole linear business again. What's inside the angle is linear. Pi x over 5 is linear. What is the derivative of pi x over 5? Pi over 5, right? The coefficient of x. If you have a linear function of x, mx plus b, the derivative is m. So the coefficient of x is pi over 5. So that's going to be the derivative that we're going to end up dividing by instead of multiplying by. So we will end up with 35 plus 5x. The integral of sine, we just think conceptually, integral of sine is minus cosine. So we're going to have minus 10 cosine of the same angle. Now we divide by the derivative of the angle. We said the derivative of the angle is pi divided by 5, so we divide by pi over 5. And then this is on the interval 0 to t. Okay. This is the antiderivative in here. So that's what we're plugging the t and the 0 into. The 35 is not part of that. So let's plug in the t first. We get 5t. And now here, dividing by a fraction, we multiply by the reciprocal, so we get negative 50 divided by pi. Cosine of pi t divide 5. Okay, so that's the antiderivative evaluated at our upper limit of integration. Now we subtract off the antiderivative evaluated at 0. Plugging in 0 here gives 0. Plugging in here gives cosine of 0. Cosine of 0, 1. So that's gone. We're subtracting. Subtracting a negative means plus. And we still have this 50 over pi thing as the coefficient. And that's all equal to 1. So that's all we get, is 50 over pi. And if you wanted to move that constant to the front, you could. Does not matter. So that is our population at time t, p of t. If you want p of 15, what do? Plug in 15 for the t, simplify it. If we want p of 35, plug in 35, simplify it. So in summary, 6.1, that stuff, all the stuff we just did. So you should be able to finish the 6.1 homework now that it's due at the appropriate time, now that it's available. 6.1. And let's go and at least do one slide of 6.2. Yeah, we'll be able to do a couple slides. So this should be a little bit of review. One of the beautiful things about Calc 2 is that we do not have to do Riemann sums. We get to do this with Riemann sums. And because it's a Riemann sum and we're taking the limit, you get this. That's all we have to do in this class is wave our hand a little bit. We don't have to deal with left endpoint approximations, right endpoint approximations, midpoint approximations, until you get past all of the calculuses and you go take some applied math courses in your engineering program. Then you'll start doing it again, but with different types of left and right are totally, and midpoint. You'll do Simpson's rule and some other techniques that are pretty cool and more applicable. The idea is the same, but a little more accurate. Okay, so if we want the area between two curves, remarkably, all we do is take the antiderivative and evaluate at the endpoints. It's remarkable. So the concept behind it is that we subdivide into a bunch of rectangles. You pick any point you want in each interval. And so that's what this x star sub k is. It's just any point in the interval. You've got your subdivisions. You create the rectangles. You add up the rectangles. That's your Riemann sum. Your Riemann sum is an approximation because you have those rectangles. It's not fit to the curve. But as those rectangles get narrower and narrower, the approximation gets better and better. And then you do the magic. You sprinkle the fairy dust called limit. When you take the limit, poof, you get exactly the area between the two curves on that interval. So this is the height of the rectangle right here. That's the height of a rectangle. This is the width of a rectangle. That's the area of a rectangle. You add all the rectangles up, you get an approximation for the area. And then when you take the limit of that, you get the exact area. Limit of a Riemann sum gives the value of the definite integral. So that's it. If we want to find the area between these regions, all we have to do is integrate on our interval the upper function minus the lower function. Upper minus lower. That's all it takes to find the area. So let's just set up these two integrals. So this area is going to be the upper function, so minus x squared plus 4x, minus the lower function. I'm distributing that minus. And then we have to find our limits of integration, which we'll do in 1 second. And then over here, same idea. The area is going to be the integral of the upper function. Can someone tell me what the upper function is here? 0. Right. Y equals 0. So then minus, and I'm going to distribute this sign value here, or this sign function. So let's just get these two set up. So there, that's how we're going to calculate area. Just integrate upper function minus lower function. In your mind, upper minus lower is the height of the, the sort of the invisible rectangle. So you would, a lot of times we'll draw a vertical integration element. We just imagine that as a very narrow rectangle. The height of it is upper minus lower, and the thickness or the width is the dx.
Did you mention x after the 4 on the first one?
Yes, I am. Thank you. Yeah, that is a 4x. Thank you. Thank you. So we'll figure out the limits of integration on Thursday. And we'll finish off integrating these. See if you can integrate them. See if you can find your limits of integration. See if you can remember how to solve systems of equations, because we'll have to do that frequently. Substitute. All right. Happy New Year.
So we have the homework for 6-1.
So, so it's all going to be due at once, but you should be able to finish it now.
Yeah, and then pre-work.
So we're going to do 6-2. We're going to finish 6-2. So we'll finish 6-2, and then we'll get through as much as 6-3 as we can. So when 6-3 shows up in 2 places, that means we'll try to get through half of these. Now you should be able to finish that homework and then read up on 6-2.
Only one thing we have done.
So my math lab, no pre-work. So my math lab homework, my math lab quiz, which are all going to be done that day, and then our work. Make sense? And so anyone that's going to stick around, I will be here for 40